sac321 number 5. If you haven't read it already, please pause the video and read it. They're asking us to find the moment of inertia of a pendulum that consists of a rod of length L and a sphere with respect to an axis 10 centimeters from the top end of the rod. Perpendicular to the page as we view it, and in fact we know the moment of inertia, I'll call it I sub r, of the rod with respect to an axis through its center of mass and perpendicular to the rod, and we know the moment of inertia of the sphere I sub s with respect to an axis passing through its center in terms of the mass and the length in the case of the rod, and the mass and the radius in the case of the sphere. The total moment of inertia of the entire system is going to be the sum of the two moments of inertia with respect to the axis through point O in both cases. So I'm going to go ahead and write that down. That's I total, I'll just call it I, is I of the rod, moment of inertia of the rod with respect to point O, plus the moment of inertia of the sphere with respect to point O. And these axes are all parallel to each other, and I'm going to get the moment of inertia of the rod with respect to the axis through O by means of the parallel axis theorem. I can write that as I with respect to the center of mass of the rod, the I sub r, plus the mass of the rod times the distance that the rod is from the distance that the center of mass of the rod is from the axis of rotation. So the separation of those two axes, one through the center of mass and one through point O. And let's go ahead and label that on here. This distance right here is what I mean by d sub r. And then we've got a similar substitution for the moment of inertia of the sphere. It'll be the moment of inertia of the sphere with respect to its center of mass right there, plus the mass of the sphere times the square of this distance from the center of mass of the sphere all the way to that axis through point O. So I'll call that d sub s, and I need the square of d sub s here. Alright, now let's figure out what d sub s and d sub r are. D sub r is going to be, it'll be half the length of the rod minus this distance that I've called A in the diagram, the distance that the axis about which we wish to calculate the entire moment of inertia is from the end of the rod. So that'll be minus A, or this was just over 2. Let's fix that up. So that's 0.50 meters divided by 2 minus the A, the 0.10. That's meters. So I got 0.25 minus 0.15 meters. I'm going to need that value right in there. And then this distance right here, d sub s, well, it'll be the total distance from the end minus this 10 centimeters. So that's going to be, total distance would be L plus the radius of the sphere, and then minus the little a there, and that's 0.5 meters plus 0.25 meters minus 0.1 meter, or a whopping 0.65 meters. Okay, we'll need that right in here. What else do we need? We need Mass of the rod is going to be in there. I think we're pretty well set. Let's go ahead with those two values. Let's go ahead and replace the moments of inertia with respect to the centers of mass with our given expressions. So we got I is equal to, and I'll tell the reader where this one came from. We're just following off on that. The 1/12 ml squared, and that's the mass of the rod, plus the mass of the rod times the dr squared, just found a value for that, plus, now the moment of the inertia of the sphere was given as 2/5 mr squared, where the m is the mass of the sphere, so I use m sub s, and then plus our last term, ms d sub s squared. And we could actually substitute values at this stage. I think I'll simplify it just a little bit, make the substitution stage just a little bit simpler. Factor out the m sub r, so I got L squared over 12 plus d squared, multiplying the m sub r, and then I got an m sub s in each of these two terms. Factor that out. That's 2/5 r squared plus d sub s squared. Okay, now I'm ready to substitute values and evaluate. Mass of the rod given as 0.5 kilograms and its length 0.5. So 0.50 meters, of course, for the length. And that's divided by 12. And then this is d sub r. D sub r we found to be 0.15 meters. Plug that in. And then I got plus the m sub s given as 0.45 kilograms. And times 2/5 times the r squared, where r is 0.25 meters. And then plus the d sub s we found to be 0.65 meters. And that's squared. So we plug all those into a calculator and evaluate it. And I get a value just above 0.22 kilogram meters squared, which rounds to 0.22 kilogram meters squared. Put down kilogram meters squared, to be honest, because moment of inertia in SI units has units of kilogram meters squared. Let's check it out and make sure that they really worked out that way. In here I got meter squared plus meter squared. That's all meter squared times kilogram. Okay, that's good. And then in these brackets I've got meter squared plus meter squared, that's meter squared, times kilogram. So that one's good as well. Add those two together and you get something that's got units of kilogram meters squared. And that does it for SAC 321 problem number 5.